Okay, hello everyone. This is the bootcamp for homework 2, which is like based on convolutional neural networks. This is like basically for image data, neural networks for image data. I'll be going through the homework 2 part 1, which is like you implement various aspects of like convolutional neural networks with NumPy. These slides were made by Parajit, one of the XTs of the course. So let's look at homework 2 part 1, what you will basically do. So we looked at resampling, we looked at convolutional layers, we also looked at max pooling, mean pooling. You'll be implementing everything in NumPy. So the first thing that you'll be implementing is resampling, which involves upsampling and downsampling for one dimension as well as two dimension. The important thing to note for this case, as well as for throughout the homework, that the for loop is to be used as less as possible. It is not recommended that you use for loops because NumPy is a vectorizing library. There are functions present that can vectorize your operation, that can speed up the execution time of your code. So for resampling, there are two ways. We can either use np.cron, which computes the Kronecker product between two matrices. I would suggest that you look up the documentation of NumPy to learn more about it. The convenient and very easy way of doing resampling is using array slicing, which is basically a functionality that's supported by NumPy, where for along a given dimension or axis of your matrix, you can define this you can define a slice of your matrix with the start, end, and step parameters, which is basically like start index, end index, and how much of a step you want to take. So if the step is 2, that basically implies that you and the start and end are like 0 and end. This slicing would give you all the indices like 0, 2, 4, 8, and so on. Try to think of how you can apply array slicing to do resampling, which is upsampling and downsampling. We will actually try to compute the required shape while upsampling and as well as downsampling. So look at the output shape that's needed and try to figure out how you can use array slicing or the np.Kronecker product to do resampling. Again, you cannot use for loops. These are vectorize operations that you can use. And you would also store the shape in the forward method because that shape would probably be used in the backward method. So that's a thing to remember. I'll move on to the next part where once you have implemented resampling, you will be implementing convolutions. Again, you can do convolutions in a loopy way where you have nested for loops, or you can do convolutions using tensor dot, which is the vectorized way, which we recommend that you use tensor dot and not nested loops, because the more loops you use, the more time it takes to run the code. With tensor dot, we don't have to like take care of all of the broadcasting and all of the matrix multiplications. Some information about tensor dot is given in the write-up, and we'll also cover what is tensor dot in this bootcamp. So tensor dot is basically a function in NumPy. In a nutshell, tensor dot actually does the convolution operation for you. So basically, when you have an image and you have your kernel or filter that you want to convolve your image with, so the intuitive approach is basically place the kernel on the image and then slide that kernel over the entire image. And then when you're sliding it, you compute the product, add those together, and to get the value in the output map. Remember that the number of channels or the number of filter maps in your filter is equal to the input channels, and the number of filters that you have is equal to the output channels. For like, if you want to revise more, probably look into the lecture slides to understand more. But tensor dot is actually a vectorized way that again does your convolutions for you. You will be only needing one for loop in con 1D and two for loops in con 2D. This is the most efficient way of implementing convolutions using tensor dot. I'll quickly explain what tensor dot does so that you guys have an idea of it. So let's say you have two matrices X and W. Let's say X is your input and W is your weight matrix. And the input X is of shapes A, comma B, A, B, and C, and the shapes are like P, Q, and R for W. We can do tensor dot when there are some dimensions along which the shapes match. So in the case when B is equal to Q, which is the second dimension of both X and W, and C is equal to R, we can actually do a tensor dot operation uh, that will take in X and W and will return the output of shape A, comma P. We can use this to do the convolution operation, which we require in conv where given the filter and the input image, you can extract that part of the input which needs to be convolved with the filter. Basically that will be the size of the filter, and then you should be able to technically use tensor dot to get the outputs for that particular index where you are present in the image. So make sure that the inputs to the tensor dot have some matching axis. Uh, and this is precisely how you can use it in convolution, because a filter only looks at the segment of the input. So if you remember, in con 1D, you can only use one for loop. That one for loop is basically to go in that one single dimension, let's say left to right. And then when you are trying to go from left to right, at each index, you would place your filter, you would do the convolution operation, and then proceed to the next index, right? You'll be sliding the filter from left to right. So theoretically, like the most efficient way to do this is to go on every index in your input, place the filter there, and use tensor dot that would directly give you the output for that corresponding index. And then you slide your filter and do the same. So this sliding of the filter is what you are allowed to use for loop. Apart from that, all the convolution operation where you multiply the values of the filter and the input and then sum them together should be done with tensor dots. And keep in mind, tensor dot can also handle the case when you have multiple filters. So let's say you have 3 filters, your output will have 3 channels as well. So tensor dot will be able to handle multiple filters along with the input image. So to understand how tensor dot works better, let's say we have a matrix with shapes A, X, C, Y, and then there's another matrix with shape X, P, Q, Y. The most easiest way to understand tensor dot is basically you write down the shapes of whatever your inputs are. You see which shapes match across which dimensions. So you see X matches with X here and then Y matches with Y. This doesn't need to happen at the same dimension location. Like X here is in the first index, where here is in the 0th index. You can define at what indexes the dimensions are common. And what would happen is, if you write the shapes like this, AXCY and XPQY, you can just eliminate the dimensions that are common. So you eliminate X here and Y here, and whatever remains from left to right, which is A, C, P, and Q, that's actually the output pattern, output shape of the matrix that you will get. To repeat again, when you have two matrices and you are trying to do tensor dot, figure out the axis along which the dimensions are equal. And once you do a tensor dot between, let's say, this first vector and second vector, first matrix and second matrix, if you list down the shape sequentially, remove the common ones, whatever remains is the actual shape of the output. This is a very good way to debug your tensor dot implementation and see how it is working. To give you a hint, when you are doing the convolution operation, you are looking at one segment of your image. So in that segment, the height and width of the filter and of your input is same, as well as the number of channels is same. So this is the reason why when you have like same dimensions along the axis, you can use tensor dot to do the whole convolution. It is not necessary that only two axes should match. You can have multiple axes matching. You need to figure out how to use tensor dot in those cases. So any doubts up till here on how to use tensor dot and how about resampling? You can probably unmute and ask.
Just I'm guessing we have to read up and tensor out, but just to get some intuition, if you had like a just a 2x2, like not 2x, like two-dimensional numpy array, what does tensor dot exactly do? Like along which axis does it do, like dot product or something? Can you explain that so that we can
Yeah.
like then we could like try to like extrapolate that to like more dimensions.
Right, right. So let's say you have a 5 cross 5 image, and then you have like a 2 cross 2 filter size, and then you want to do 2D convolution in this, because you have a 5 cross 5 image. The 2 cross 2 kernel would like move from left to right and then go to the next like come down and then go again from left to right and so on. So this is a 2D convolution. So think about how the convolution is done. You have your input, you place your filter on the index where you want to do the convolution, which is, let's say, at the top left corner. You place your filter on the image, and after placing your filter, the whatever computation that you do from here, which is basically multiplying the weights in the filter to the values in the input and then adding up together to get the final value. This is accomplished by TensorDot. Again, if you just need to get your input image, place the filter on the image, and at whatever index you are placing it, the whole convolution computation can be done using TensorDot.
Okay, and in this example, like when you have 5x5 and 2x2 filter, what would be the output shape?
Okay, so here's the thing. You would be running a for loop for this. So let's say you are placing the filter at the top left of your image. So your filter is 2 cross 2. You are looking at a 2 cross 2 segment of your image, and then you are doing the convolution of it. So that will give you one value in the output. You store it, then you move the filter, do the convolution operation again, and then you get the next value. So basically, how the convolution works, when you are sliding the filter, every time you get a new value. So that is what is being computed by TensorDot. So in the end, you would have the output matrix shape would obviously be like, I think it would be like 3 cross 3, because you have a 5 cross 5 image and a 2 cross 2 uh, filter. You would have a 3 cross 3 matrix in the end, but you would initialize that matrix with like zeros or something, and then for each index you would compute the convolution value and then put it in the appropriate index in the output matrix placeholder. And then once you are finished with the for loop, you would have your final output shape.
Got it. Thank you.
Yeah. Again, so just to clarify, this was just for an example where you only had one channel image. When you have two channel image, the filter would also have two channels, but we would only get one channel output when we use one filter. Then if we increase the number of filters, you would get as many number of channels in the output. The whole operation can be done by TensorDot. When you have multiple filters and when you have multiple input channels, the whole convolution can be done by TensorDot. You would only need to slide your filter from the index positions. That's why in con 1D you slide in one direction, in con 2D you slide in two directions. Uh, so that's what the for loop is for. Once you are at a particular index, the whole convolution operation should be done using TensorDot. I think there's also this other NumPy function called einsum. It also functions in the same way, but I feel TensorDot is more intuitive, because when you just write down the shapes, and you would know what the output shape of the image should be. So you can like try to configure the input shapes or the output shapes, and then try to figure out how to use the TensorDot operation. That's a easier way to debug as well as understand how the convolution is actually working. So I think I'll move on if no one has questions. So we'll be implementing both con 1D and con 2D as well. So try to understand each step while doing con 1D. Con 1D and 2D are very similar, because you are actually doing the convolution operation. You're just doing that. It's just the dimensions have changed. Like you have one more dimension to cater to. So when you're like transitioning from con 1D to con 2D, you would need to account for the extra dimension and probably do a little bit extra. That's also just because to account for the extra dimension. So try to implement con 1D with tensor dot, understand it, and it would be easier to implement con 2D then. Once you have implemented the con layers and the resampling layers, we have pooling, which will be like max pooling and mean pooling. Lectures have the basic pseudocode, which is like obviously there in the slides. This is again another task where you might need many loops for this task. Uh, so let's say for max pooling, if you remember from the class, we for every index, when we place the filter, we actually try to get the max value that is present in that filter, and then that's our final value, right? So if you remember in the pseudocode, we find out the index where the max element is present, and then once we have that index, we then pick out the max value. The reason why you are tracking what index you're picking your the max value is because when you are doing back propagation, it would be a help. So for more details, probably just go through the handout and the write-up. But since we need to keep track of index for max pooling, there's a necessity to use for loops. You can do mean pooling with convolution. It's possible, but it's up to you to like come up with an efficient solution. Because let's say you have a 2x2 filter and then you are trying to do mean pooling, you can initialize the weights as 1/4. And if you initialize the weights as 1/4, you can essentially do a convolution, and that would give you the effect of mean pooling. Uh, and the rest is up to you to figure out how stuff works. So look at the handout for more details. So let's try to quickly understand the gradient propagation and what happens for convolutions. So let's say we have an input a single channel input A of height and width. There are two kernels here. So for each kernel, the number of channels should match the number of channels in the input for each kernel. So for each yellow block also has one channel because the input has one channel. When we have two kernels, we would have two output channels. For the number of kernels is equal to the number of channels in the output. So that's why we have two kernels, and the output has two channels. So so what happens is we try to draw the influence diagram. Basically, the kernel and the input gives us the output. Where for let's say I j in the input, both the kernels act on that input and then give different values in different output maps. So now when you have drawn the influence diagram, it should be easier to figure out that a small change in this input A will cause a change in both of these output maps, because we have both kernels interacting on every element of every element of A. So this is the computation graph that's present. We will so for back propagation, what will happen is this is how the forward process will happen. But when we do back propagation, we would need to sum up the gradients when we are at, let's say, from output Z to the input. More on how the gradient back propagation works in CNNs will probably be covered in tomorrow's session as well as in next week's lectures. So once we have the basic building blocks of building a CNN network, which is like convolutional layers, your resampling, and then your pooling layers, it's time to build your CNN models. That's also another task where you'll be building a CNN model based on the layers that you have. More importantly, we would be focusing on building something, a CNN that is something like a scanning MLP. If you should probably look at the appendix of the handout to understand scanning MLP. But basically, what happens is con 1D layer sees the input as like it can take an input when, let's say, the input is 3 cross 5. The con 1D can see this as a two-dimensional input, whereas when for linear layers we need to flatten this input so that it can be read, it can be fed to a linear layer. So what happens in scanning NLP? Considering let's say we have an input of we have this input and then it produces two output features for and the MLP looks at the every three elements. So the size is like 3. We would be computing the output at this. We would be actually be flattening these 9 inputs and then passing it to the MLP, which would be computing these two outputs. So the MLP would go to the next, slide over, and then slide over, and this will go on. So what's actually happening? The kernel size is 3. When at every instant we are flattening that window of inputs into a one-dimensional vector that can be fed to MLP to get two outputs. The MLP produces two outputs for every input that it receives. So this kernel moves ahead, and then we get another set of outputs. It moves ahead, and we get another set of outputs. This is same as covered in I think Mondays and Wednesdays lectures. So now when we have done the sliding from left to right for this input, we have this corresponding output where there are two outputs for every window size that we have looked at. So what happened here? We had 9 inputs to our linear model MLP that gave us two outputs. So this we can think of this MLP as a linear layer of 9,2, where the input size is 9 and the output size is 2. What happens when you use a convolution instead of a linear layer? Given 3 channels as input and then 2 channels as output, we had the kernel size of 3 and a stride of 1. We have actually transformed the linear layer, which was like 9,2, to a con 1D of the following parameters. Con 1D because we are just sliding from left to right in one dimension. So this is how a scanning MLP can be like thought of as con 1D. This is something important because you would be doing CNN as simple scanning MLP and CNN as distributed scanning MLP as the last task in your homework. So it is important to understand how you can think of the scanning as scanning MLP and then try to construct the convolutional network that does the exact same thing. So once you have all of this, you build the CNN model. We just call the layers that you have implemented previously. The only thing that we have to think about is what is the final linear layer. So when you flatten, what would be the shape of it? So when you go through every CNN layer, you can actually compute the height and width of the output of each layer. Once you have that, you do that computation, and in the end, you will know what the final dimension of the flattened output will be. That can be passed as the input size to your linear layer. Important thing to keep in mind. So you would be copying the linear.py, activation.py, and loss.py from homework 1P1. So while you copy it in this homework, you might probably run into issues of closeness error or like true divide error, or you might encounter errors of like overflow or underflow. That is probably because you did not account for that in implementing the tanh activation function. Tanh is an exponential function, so it can overflow and underflow depending on x. There are various tricks that you can like you can modify the formula that will account for overflow and underflow. However, you can just directly use the tanh function of NumPy to calculate the tanh value, and that's very easy to implement. So keep this in mind. If you did not implement your tanh function considering overflow and underflow, probably you can change that to np.tanh. So I think that's all I have for homework 2 part 1. If you guys have any doubt, feel free to ask here. And if not, we can probably move to part 2.
Raghav, I think we have one question on the chat. Um, it says, could you please give an example of the last linear layer that you just told about?
Yeah, sure. Sorry, I didn't see the chat. Okay, so what happens in a scanning MLP? For every window of your input, you probably this slide is better. For every window of your input, you flatten that and then you pass it to your MLP. And then this window can proceed forward, but for every window of your input. So consider this as the example in class where we were trying to figure out if welcome is present in that audio. And let's say this was the window where welcome will be present, and then we are sliding this window and then trying to find out if welcome was present in this audio or not. So if you want to process this as a scanning MLP, you would want your MLP to actually take in this input. Since this is a two-dimensional input, you would need to flatten it so that the MLP can take that as an input and then give you two output features. This is the design of the MLP, that it would give you two output features. We also did this in homework 1 part 2 where when we had the MFCCs, we actually, once we had all of the MFCCs, we flattened them and did all the padding and all the other stuff. But apart from that, so for giving input to your MLP, you need to uh, flatten this in this region of your input and then pass it to your MLP. And then this will probably give you whether welcome was present or not. So what's happening here? This let's assume this MLP is just one linear layer. The linear layer is taking in 9 inputs, which is basically 3 cross 3, and then it is giving you 2 outputs. So we have the linear layer can be defined as 9 comma 2, which is like you can have like a 9 cross 2 weight matrix that will work on this, and then that will get multiplied with this input and then give you two output values. So this is where the linear 9 comma 2 comes in. If you attempt this problem as a scanning MLP. Now, instead of doing scanning MLP and then like sliding the filter, and every time when you slide the filter, you get a new set of outputs as shown here. What if we can, so this is basically when you have done the sliding from left to right, and let's say you have all the outputs here that's shown. What happens if you do just a convolution instead of a linear layer? There are 3 input channels here, and we have 2 output channels. We knew that our kernel size was 3, that is the window of finding welcome in the audio. And our stride was 1 because we were moving ahead by 1 step every time. So we can use these parameters to construct a con 1D layer with like in channels, out channels, and so on. That will give me the exact output as my MLP did in case of when the MLP was linear of 9/2. So let's say this, so this is to illustrate how a CNN can be thought as a scanning MLP, where instead of using, you can use either linear 9/2 or you can use con 1D to do the exact same operation. The difference, however, is in the number of parameters. Obviously, when you do a con operation, con layer, that has significantly less parameters in the cases when you have like large inputs. That was also like covered in class. So this is kind of an example of where how you can treat a CNN or how you can treat a con layer as a scanning MLP, and vice versa, how you can think of scanning MLP as a con layer, con operation. So is that clear? Okay, you got it. Thanks. Okay.
Okay, I think we can
Okay.
move to
Yeah. Yeah.
part
Thank you for
2.
your time. Yeah.
Okay, so yeah, hello everyone. We are continuing with the part 2 of the bootcamp. So a quick advice would be that start the homework early. I know every course in CMU says that to you to start homework early, and many of the courses you might be able to do a homework on the last day. These homeworks, especially the part 2s, are designed in a way that it's impossible to do it in the last day. And homework 2, so you have already done the training for homework 1. Reaching the early cutoff might not take too much time, but once you have crossed the very early deadline, reaching the high cutoff is a huge commitment of time. So if you start early, you can actually just let your model train, and while you can do homeworks for other courses. But if you start on the last day or last couple of days, you'll just be sitting in front of a computer waiting for the model to train and being anxious because you don't know if you'll actually cross the cutoff or not. So do start early, and reaching the high cutoff of homework 2 will take significantly more time and more efforts than what was for homework 1. Additionally, you cannot copy code from anywhere. So as you move to our homework 2, you'll find many architectures on the research papers like ResNet, Convex, etc. We'll cover those in this bootcamp also. You can read the paper. If you want, you can even see the code implementation they have on GitHub, but you cannot copy that code. So the suggestion I give to students is, if you want to understand how it works, and for some people, paper makes more sense. Some people understand better by reading code. So whatever works for you, good. But when you're writing your own code, do not look at the code of the paper. When you're writing your own code, write it just by reading the paper or write it by your own memory. If you have photographic memory, then try to avoid reading the code in the first place. But yeah, your code must be your own. Even among study groups, your code cannot be same. You all have to implement, even if you're implementing a standard architecture, each of you might implement in a different way. And those variations actually might help you learn more about how that architecture work, especially when things don't work and you have to debug stuff. And finally, I know many of us students have been asking about the compute resource. We have applied for AWS credits for $150 for each student. You can use those credits for either your project, training your models in the project, or you can use it for homework. That's entirely up to you. We will try to get some additional compute for projects, but that's tentative right now. And additionally, CMU has this thing called Virtual Andrew. It's a Windows operating system, but it comes with a good GPU. So if you are training efficient models, which means you are training models with less parameters, then you can pretty much use this device to train most of your models. And then at the end, you might ensemble them together to cross the high cutoff. Again, just as an example, one of the students in this very batch for homework 1 part 2 trained a model with just 5 million parameters. So even though the limit for homework 1 was 25, she just made a 5 million parameter work and reached very close to the high cutoff. So it's not always to train the biggest model in the most amount of data. You can actually find better ways of doing things which are much more smarter. And that way you also use less compute, and you will not have to burn half the Amazon rainforest to just do your homeworks. So yeah, that's the logistics side. We can probably move to the bootcamp now. The problem that we have for homework part 2 is about phase classification and phase verification. So how phase classification works, basically assume you have a class of 250 students like ideal, and we have some camera somewhere which is focused not on the professor but on the students. Can we use that kind of thing to figure out how many of the students are actually present in the class? So for that, we'll have multiple images of each student, let's say through their different past records or social media platform, whatever. And we are training a model to, whenever the model sees a new face, it will try to classify it as one of the 250 faces that it has trained on before. So it knows that every face it will see will obviously be of one student in the class, because all of you have registered for the class. It just have to figure out which person it is. So that's classification. You already know you have a limited number of classes, and for every new test data, you're trying to classify it into one of those 250 classes. Obviously, in our actual homework, you'll have many more classes because you will have a large number of people. Phase verification is slightly a different problem. Think of it like if you're using a Windows laptop, you might have Windows Hello. Or if you're using an iPhone, you might have face recognition on the iPhone. So it's more about, if I show you two images, are those images of the same person or different people? Now, the challenge here is, if you are making face verification login for your smartphone, you may not be able to train on user data. I mean, user will buy a smartphone from the market. You don't know who the user will be, while as an engineer, you are building your face verification software. So you need to be able to figure out within a very few images, one or two or maybe, what the user looks like. And every time the user tries to sign in, you should be able to tell, is it the same user or is it a different user? So that's face verification. So for face classification, we'll have a feature extraction model, which will find embeddings. Now, this might look like a jargon to you. Basically, if you attend the lectures, you'll understand the convolution networks, even though in 2012, when AlexNet came into picture, it was used for image classification. But later on, people realized that convolutions are not just good for image classification, they're actually able to extract features in those images. Now, those features, just for the sake of understanding, could be your facial features, how your the shape of your eyes, the shape of your nose, etc. And then those embeddings that come out of the convolutions, we put them in a linear layer, and that linear layer gives us probability of every class in our initial training set. So that's classification. For verification, we'll have two images. We are shown image 1 and image 2, and we have to figure out how similar they are. So if we did a good, again, like I said before, if you're making a facial login tool, you will not always have training data for the user who would actually be using your software. So you need to be able to learn to extract features from random facial images and then work it on a user who is completely unseen. And hence, that's where you start to focus on the fundamental aspects of a face image instead of trying to find are the two things belong to the same class. So yeah, like you are seeing two pictures here. One of it belongs to the prof. I hope you can recognize which one. And you have to tell how similar those two images are. So if you have trained a classification model properly, you can actually use the classification model, the initial part of the classification model, the feature extraction, and then try to compare those features. So can you go to the next slide? So here we know that we have an unknown image on top that we want to figure out, and we have two known images. So we want to we'll check the similarity of the unknown image with every known image in our training set. And then for every known image, we'll give you a similarity, how similar these faces are, how different they are. And that's how we'll tell if those two images come from the same person or they are different people. Next slide. So the workflow, you should start with the classification task. I mean, if you want, you can do classification and verification completely independently. But what I would recommend as a TA is start the classification task, train a very good classifier, try to reach as close to the high cutoff as possible, and then use this very same classification model with the checkpoint and just remove the final feature layer. So if you remember the architecture, the very last layer is a linear layer, which will give you the probabilities of each class in your training set. So remove the last layer and just use the entire convolution backbone, and then try to see how can you customize the same network for a verification task. Now, when you're doing verification, note that the people you'll see in the verification dataset might not be available in the classification training dataset, but they are still human beings, so they'll have similar facial features, and we can extract those features out of their faces. So except the very last layer of classification, all other convolution layers are learning something more fundamental about a face beyond just a classification task. And then we can talk about what loss functions you can use separately for verification, which can help you fine-tune the model that you train for classification to do the second job. So yeah, Jill, for you. Jill?
I'm sorry, I was muted. So we basically have three building blocks that we would consider for our part two. And we would categorize it as following. So the first part would be the input image and transformations. and then comes the choice of model, and then actually training the model. So one of the reasons why we consider that the input, image, and transformations is one complete building block for this project is because it affects your performance a lot. And as we have discussed, like our major aim over here is to be able to classify or verify faces or images in general. And we want our model to generalize better. So you might be given like a couple of images, but the test images are going to look like very different from that. So what could you actually do in order to make your model generalize better? So we'll work with transformations for that. One of the examples could be color jitter, which actually you can see over here on the slide, like it adds some variation to your colors. And then there's random perspective. We can actually see a lot more over here in the link that's provided. Sorry, I'm not able to. Sorry for that. So here we have the documentation for the transformations, and you will be able to explore a lot of transformations over here. But what is important over here is to figure out which of these transformations will actually be important for you. So we want to add variation in the data, right? We want to account for the extra brightness that could come up in the test set, or maybe in one particular image, the person is looking at one side and then the other one, the person is looking at some other side. And we want to account for that and train our model to generalize better. So we might want to add some grayscale or some random augmentation, which is also possible, and some rotations. But do any of you have any idea about what kind of transformations would or would not work? You can just unmute at this point or whenever, like even if you have questions.
So I guess things like translation, rotation, and maybe perspective transformation will work, but not things like inverting the color.
Mm-hmm. So what do you mean by like inverting the color?
Like
Not
just
work.
inverting the color of each pixel so that like red becomes green plus blue, which is yellow.
Mm-hmm. Okay. So that is one particular thing that could be argued, like whether it works or not. Another very intuitive thing would be a vertical flip. So for example, over here, we have all these images, and one over here is inverted, like completely upside down. Now, one thought about this could be that in the test set, it's very unlikely that you would see like an image that is upside down. If you were imagining, like, for example, students in the classroom, it would be difficult to see them upside down, sitting down, right? So that is something you would probably avoid using for transforms, but stuff like a normal, like a horizontal flip, or a color jitter, or other, like, say, random augmentation also has, you could probably like look at the documentation there and figure out what would actually work, and sort of work with your intuition also at this point. So you have the link over here and you could explore further. One of the very common issues that come up when you're trying to use transforms is this type error, which says that input tensor should be a torch tensor. And this is a very common issue that happens, and so it's on the slide. One thing that you might want to know at this point is that you need to check the sequencing of your transforms. So some of these transforms require the input to be a tensor, and so it should go after the two tensor transform. And this is something that you should be able to find in the documentation and also while you experiment. And there are some of the transforms that you would actually need to have to learn what they take as input. For example, normalization, you would actually have to go back to the data set and find the mean and the variance. And if you said it wrong, it's not going to work for you at all. So it is something that you need to look more into.
Yeah. So to connect this back to what you have been doing with homework one, transformation is similar to data augmentation concept. So some students try to implement random noise in your input data, or added frequency or time asking for homework 1 part 2. Now, the whole point why we even need data augmentation is because our training data is limited and our test data might be coming from with a lot of variations. So if we try to add some sort of noise or augmentation, we might force the model to learn things which are actually relevant and try to ignore things which are irrelevant. For example, we want to recognize this person's face. So we may not want the model to learn the background. Like there have been these kind of silly examples that, hey, people wanted to use machine learning for hiring purpose to see which candidate is better. And machine learning picked up that if there's a book in the background, the candidate is a better choice. So to avoid these kind of biases, and to make the model focus on exactly what we want them to focus on, we add these augmentations. And again, it also depends upon where your data set comes from, where your training data set comes from, where your test data sets come from. For example, if you're trying to make something work with a smartphone camera or a web camera on your laptop, a user will be using the laptop or smartphone in different lighting conditions. The room light will change, there might be sunlight, they might be doing it in a dark place, etc., etc. Time of the day. So now how do you make your model invariant to the light environment of a user? So you have to figure out which transformation makes sense for your particular use case. Now in this homework, we didn't give you a use case, we just gave you a data set. So you should explore the data set and try to figure out what transformations make more sense, and you compare the variations in the training and the test data set, and then decide a strategy. We won't tell you what strategy you should proceed, but if you want, you can come and discuss with TAs about, hey, I'm thinking of this, and then maybe we can discuss if it makes sense, or there might be some consideration that you should take care of, etc. So yeah, that's transformation. Let's come to the building blocks. So we did the part one. The middle part is what architecture should we go with? Now, next slide. So before we talk about the architecture, there's a new concept for convolutions, which is about residual connection. We slightly touched upon it in a hackathon for homework 1, but for homework 2, this will become the most prominent thing. So first of all, why do we even need residual connection? If you look at conventional neural network architectures, it's like you have a series of layers. Every layer is fully connected to the next layer, and it's a very sequential thing. But the residual connection is, what if we add a skip connection? What if we skip 2 or 3 layers and put the input of let's say layer I and add it to the output of layer I plus n? So that's how residual connections work. Why do we even need that? So if you look at your activation functions, which add nonlinearity to your network, you will not always have a good gradient. And you need gradients to tell which direction you should optimize towards. Your backpropagation needs gradients. So if you're using, let's say, a ReLU function, so a ReLU function on the negative side is flat. So no matter how much is the difference between your desired and your actual prediction, on the negative side, you don't get any information about which direction you should go towards to optimize. Similarly, if you have a sigmoid function or a tanh function, so they give you good details in the middle region, close to the origin. But as you go away from origin, the activation function saturates. And by saturation, it means your gradients will become less and less prominent. So this problem is called vanishing gradient. Can you go to the next slide? Yeah. So to resolve the problem of vanishing gradients, and there is another aspect, or the other way around of vanishing gradients, if your gradients become infinitely large. So to avoid these problems, we bring this concept of residual network. And this thing actually was figured out empirically. People tried different things, different architectures, just like you were trying different architectures for homework 1, people tried to do that for convolutions. The problem with convolutions was, as you go deeper and deeper in the network, as your depth increases, this vanishing gradient problem becomes more and more prominent, and then it limits how deep a network you can train. But if you add these skip connections, and what was found was, if you skip like 2 layers or 3 layers, you're getting good results. And then later on, people try to understand from a theoretical standpoint why skipping 2 connections is optimal and skipping like 4 connections or one layer might not be optimal. So there's enough literature on this. I would suggest you to read papers and understand from a theoretical standpoint why this work. So yeah, so the original paper proposed 2 different kind of blocks. So if you start with any paper, any latest architecture for the on computer vision side, the architecture itself might look scary. So focus on the blocks, what new block they propose. And the ResNet proposed 2 blocks, basic block and bottleneck block. And okay, is regulation in the form of weight decay? Okay, so we will come up to that question. Let me just cover the block first, and then we can talk about it. So yeah, you have, so the 3x3 is your kernel. What is the dimension of your kernel? And then you have how many channels you have left with. So the channels in an image, when you start at the very beginning, you have 3 channels. Let's say you have red, green, blue. And as you do convolutions, you will reduce the number of pixels you have in your image, and you will increase the number of channels. So yeah, so the basic block, it pretty much keeps the number of channels constant. And you'll have this 3x3 kernels, which will work upon the input image. And you will have a skip connection going from, like, you will have a skip connection skipping 2 layers. So think of it this way: you have input coming in, let's say call it X. You put it through first set of convolutions, then you put it through second layer of convolutions. The output Y, you simply add X plus Y, and then you do activations, and then you go to the next block. So this is the basic block structure. The bottleneck block, it tries to reduce the number of parameters that you will be using on the block. So it changes the number of channels you have. Now the thing is, you are adding input to the block with the output of the block, which means whatever you do in between, at the output level, you have to come back to the same number of channels as the input, or else you won't be able to add those 2 things. So think of, a usual example is that you have a 256 channels input. You bring it down to 64. You do 1x1 convolution, 3x3 convolution, and then 1x1 again, and the output again becomes 256, and then you add it. So read the paper, try to see what is the difference that you get out of basic block and bottleneck block from a empirical standpoint, why you have 2 different blocks and what will work better where. So next slide. So these are the examples. Now, just to make it simple for you, instead of talking about this from a convolution standpoint, we'll talk about it from a linear layer standpoint. Think of your homework 1, and think that if you were trying to implement a residual connection in homework 1, how would your code look like? And once you understand from a linear layer standpoint, maybe understanding the convolution side will be easier for you. Next slide. So yeah, on the left-hand side, you have the init function, and on the right-hand side, you have a forward function. This looks exactly what you have been doing in PyTorch. So if you see in the linear layers, the number of hidden layers stay constant because we're not increasing or decreasing the channels. Now, because we are working with linear layers, and I talked about like homework 1 concept, you have a 1-dimensional input, and you have 1 channel. So you have these 2 dimensions. So we are not increasing the number of channels at all. So you have those 28 frames so the frame attributes for each MFCC, they'll remain same in this entire architecture. And in the forward function is where you implement the residual connection. So the input A0 is stored as it is in the beginning itself, and then you put A0 through the first set of convolutions. So here we are doing actually linear layer. So you put A0 through that, you do batch norm, you do activations. Then the output of this first linear layer, you put it to the second linear layer. Again, you do batch norm, you do, but when you're doing the final activation of this block, you add the initial input also. So the output of the second layer's batch norm is added to the initial input, and then you do the activation. This is how the basic block looks like. The bottleneck will make slight change. In the bottleneck, you'll increase the number of channels in the hidden layer. So that's how you multiply it by 4. Now, again, look into the paper. See why it is 4. Can it be 3? Can it be 5? So how do you decide this number? So yeah, can you go back to the code? Yeah. So again, look at the forward function. You had the input of this block. You stored it as it is. And then you sent the same input to the first linear layer. You did batch norm, you did activation. Then you went to the second linear layer, batch norm activation, third linear layer, batch norm activation. But the activation of the third linear layer, that's where you're adding the initial input to the output of the batch norm. And look at the dimensions of that linear layer. So the very first linear layer, the residual layer has a number of hidden layers as multiplied by 4. So the dimension of that residual and the dimension of the very last linear layer will have equal number of channels. That's how you can add them. Okay, so again, this is just from the initial a few slides earlier. This is how you can compare the basic and the bottleneck block. In one case, you are keeping the number of channels constant throughout your progress through the network. In the other side, you are trying to create something of a bottleneck. Think of like if you have water flowing through a pipe, and you try to reduce the diameter of the pipe midway. So you create like a chokehold, like a bottleneck. That's how this name comes for the bottleneck block. Okay, so what we talked about so far was a block. Now you put these blocks together into, let's say, something we call as like a stage, and then you'll have multiple stages in architecture. That's why the overall architecture looks so big. And again, because we are using residual connections, we're able to go very deep in the architecture. So the convolutions have already been covered in the lecture. So I'm assuming you already are aware of what is a layer, what is a channel size, what is a kernel size, how does stride work. And if you actually have done part 1, by the time you start part 2, you will understand, how do you use down pooling and up pooling to convert a stride 1 into stride 2 or stride 3. So we already talked about ResNet blocks in a bit detail. There are multiple slides which will also talk about convex blocks and mobile blocks. So I'll leave that for you to read later. We'll just cover convex from a very high level in this bootcamp. And these are not the only blocks you should look at. I would recommend you to go through the literature. Many new blocks have been proposed, and many of them might give you really good results for the homework. So you should do a literature survey for this homework. Try to find what all is out there and play with it. And you might even have to change a few things in a block. Let's say certain normalization might not work for you, so change it back to something else. Certain activation might not work for you. The activation was proposed in the block, but for your data, different activation is giving better results. So you will have to even play with the structure of the block itself. So yeah, the architecture is divided into two stages. And like I said, and each stage has blocks inside it. So when you're implementing your network, I would recommend implementing a separate class, or at least I would recommend having a separate class for the block, and then a separate class for network, where you are calling objects of that initial block class. Okay, next slide. So, and then your network class could look like something like this. You'll have an initial stem thing, and then you'll start with stages. And finally, you'll have a linear layer, which is a classification layer, which will reduce all these channels into the number of classes you have. Okay, this is more like a generic guideline. It's not hard and fast rule. So when you're reading the paper, look at where they are downsampling something. And again, you would know how upsample and downsample works if you have done the part 1 of this homework. So especially with bottleneck kind of blocks, you will see downsampling happening, and they will change, how many channels you have, the dimension of your input and output. So just when you're reading any architecture, do keep note of wherever they are adding an additional downsampling step. So this is the architecture we just picked up from the paper itself, and based upon how many layers you want, they propose certain standard architecture sizes. Interestingly, because we have a parameter limit for this homework, many of these architectures might not work for you. And this homework, what we expect out of you is you do ablations, you use those block concepts that they have proposed in different papers, not just ResNet, and then try to build your own architecture. So let's say the 18-layer architecture, let's say if it has lesser parameters than our limit, might not give you good results. And an architecture that you might build by doing the ablations yourself might actually be much better for this data set than just picking up the smallest standard architecture. And the biggest standard architecture might not come within the parameter limit. Next. So yeah, I'm reading the chat questions. I'll try to keep them at the end. That way we have a single flow in the video for the people who are watching it later. So yeah, convex block, they changed how we are doing the convolutions in the very beginning. So instead of a 1x1, they said, let's start with a 7x7 kernel and then have 1x1 later on. Why did they do that? You can read the paper about what was their explanation of going this approach. And the way convex came into picture was after convolutions, attention was something people started talking about. And then a paper came which was like, attention is all you need. So don't use attention with convolutions or recurrence, just pure attention can get the job done. And that's how transformers, etc. came into picture. And then the entire computer vision community was focused upon using transformers because that became the cool new thing. And people started forgetting the basic convolutions. So another group of judges said, you can use those same convolution blocks and build something which can get you close to the performance of a transformer. You just train them in a much more modern way. You change the architecture a bit. And that's how the paper of convolution came into picture, because they wanted to make convolutions compete with transformers. My advice to you would be, don't all these, which architecture is better, how do you compare different architectures, etc. All these comparisons have been done for the ImageNet dataset. Your dataset that you're working with in your real life project may not be ImageNet. It might be something else. So don't simply go with whatever is the best for ImageNet. Do your own experiments to understand what kind of architectures or what kind of blocks will work better for your specific use case and specific dataset. Okay, next slide. Yeah, so this is okay. Maybe it's not a very new paper because it was, I think, 2020, but it's still a good paper that you should read. I would recommend implementing the ResNet block first and then reading the convex. That way the convex paper will make much more sense to you. So the convex tiny has less than 35 million parameters, but the parameter limit for this homework is 20 million. So you will not be able to use that either. The recommendation is from the previous semesters. We'll probably edit the slide later. But yes, this semester, based upon the feedback from students that we received, we wanted to learn all these blocks of building blocks that have been coming up with in the new papers. But at the same time, we also wanted to figure out how the researchers are able to come up with new architectures. So you use those blocks as your starting point, but instead of just simply taking in an architecture which is standardized in the papers, you try to come up with your own architecture. And hence we have a parameter limit which forces you to do ablations and come up with a new architecture altogether. So yeah, one of the things that the convex changed many things. Like instead of bash norm, it tried to implement layer norm. Instead of ReLU, there is a new activation function called GelU. To know what GelU, so GelU is so like ReLU was a simple thing. Like you can plot ReLU in a graph. You have on one side it's a flat horizontal line, and the other side you have a, let's say, y equal to x kind of line. GLU, on the other hand, is a probabilistic activation function. What is a probabilistic activation function? I would recommend you reading this paper that I just mentioned. It's a recent survey on different activation functions. So just go through it. You will probably understand how GLU works better. And it might also give you ideas about new other activation functions, which might work better for you. So yeah, here's the architecture for Connext, and it's compared to ResNet. Again, you look at you have the initial stem, then you have these stages, and then you at the very end, you again have a linear layer. So yeah, next. Mobile block was also designed, like in the very name of it, they wanted to make computer vision work with smartphones. So smartphone, obviously the compute resources that you have is much less than what you have in a laptop or on cloud. So we wanted things to be much more efficient. And that's where they brought in new concepts, about what is a regular convolution, what is a depth-wise convolution, what is a point-wise convolution. The hidden slides will go into more detail about this, but we can probably give you a brief summary about what these things are. Yeah. So in a regular convolution function, you are mixing information from both the pixels. You have a two-dimensional matrix of pixels, and you have multiple channels. So you reduce the pixels and you increase the number of channels. That's how the normal convolutions work. The depth-wise convolution focuses only on the pixels side of things, while a point-wise convolution focuses on channels. So, like I said, the slides cover this in more detail, but you can think of these as are you going to mix information from across both, like all the channels and all the pixels, or would you only focus upon the pixel side of things, or would you only focus upon the channel side of things? Yeah. So like I said, ResNet is not the only thing that you should, ResNet block or Connext block or mobile net block, those are not the only things that you should look at. There are many new blocks like SENet, EfficientNet, etc. So when you read these papers, and there might be papers that we have not mentioned here, so just go to Google Scholar, look at different papers which are based upon convolutions. You cannot use attention in this homework. You cannot use recurrence in this homework. You're only allowed to use convolutions, linear layers, convolution layers, and obviously normalization and activation. So look at any block which only uses convolutions and see how it performs. So the paper will talk about how it performs on ImageNet. Obviously, your dataset is different, so you have to still try out and see if that kind of performance translates into a good performance for your homework also or not. And don't look at these as individual things, because we want you to build your own architecture. Maybe combining blocks would give you a good result. Let's say you combine one block from ResNet and one block from Connext, something like that. So mix and match stuff and see and do ablations. And just like we covered how to do ablations for the homework one, try to build a strategy about ablations and divide it among your teammates. So we will cover, the next slides G will talk more about the training side of things.
Right. Just to add to that, like if you want to sort of figure out how to like mix and merge the blocks, you could also refer to some of these papers. Like ResNext is a combination of ResNet and Connext, as Sarthak suggested. So you should try your own things, but if you just want to see like how they're incorporated, you can definitely check those papers out. So we finally come to the last part of our blocks, which is training the model. You should now be like very familiar with this particular step, because you've already done a homework one. So a lot of it would be familiar to now by now. But some things will change in this homework, and that is your intuition of overfitting. We have seen a lot of people coming in office hours with saying that we have trained our models for just 20 epochs and we are not able to reach the high cutoff. First of all, you need to leave the thought that 20 epochs is a lot of epochs, because you'll have to train a lot more. Apart from that, in homework one, you would have probably seen your validation accuracy and your training accuracy to be on similar lines, with less difference between them. But over here, you might see that your training accuracy has hit like 100% already in 10 epochs. and you would say that, okay, maybe my model has started overfitting now, and you would probably stop running it more. But that is not actually the case. You should probably go and read up more about why this happens, and I would leave that to you. But it we have seen, and recent research also finds that in some of these problems, the training accuracy would hit like 100% in 10 epochs, and then the validation accuracy will still like continue to increase, and until like a further epoch. So only when your validation accuracy sort of starts decreasing, or sort of starts converging and does not increase anymore, would you probably look for more change there, and you wouldn't like just conclude that your model is overfitting. So that is one thing. So, and in this particular homework, your learning rate schedulers and other things would play a lot more important role. So I think this particular table on the right side has been taken from the Connext paper, and these are like the important things that they noticed had a different, and they also have the values over there. I think some of this we have already seen in the first homework, like the optimizer. Hopefully you guys have played around with different kind of optimizers by now. And we have seen that Adam W and SGD have worked very well with this homework, but we would definitely suggest trying out others as well. If you have worked with Adam or Adam W, you would have sort of experimented with weight decay also. But if not, like this is a good time to start using weight decay and see how it works better. There are a lot of other things like that would affect like the random augmentation, which is also part of PyTorch, which you would want to know. Label smoothing is something that you would not be familiar with by now. Label smoothing would be helpful in this case. So how we have our classes right now is we would probably have it like one hot encoding or something of the classes, where the true class is given like a value of 1. But what label smoothing does is that, say you have a label smoothing value of say 0.2, it would allot the correct class or the most probable class as a 0.8 probability, and distribute the remaining 0.2 to the other classes. And so it sort of smoothens it out. And so it is good for regularization in general. So that could be something that could be important. Stochastic depth again is so I think we got very familiar with the idea of dropout in the previous homework, and we saw how that helps. And stochastic depth in this case is similar to that in some way, that if you have like a high enough value for stochastic depth, you would be like ignoring the value of one complete output. So there could be cases where you are just taking the output of the residual connection and not the other connections. And so you would have to like sort of play around with the trade-off of this stochastic depth value. There are a couple of more things like gradient clipping and different type of normalization, drop block and stuff. We definitely recommend going over the papers and see if you want to implement any of them and experiment. So again, like, yes, this particular homework will need a lot of ablations, and so now is a good time to work with your team and divide everything. So now, like till now, I think like we've talked about the classification, and that is similar to the previous homework in that you have to come up with your own architecture, and then you have to find a way to train it. But what this homework also has is verification, and which is different from classification, and we saw how in the first few slides. So additional steps would be required in order to get good performance for verification. So we see how we used the feature encodings or the feature embeddings that we learned from our classification model, and check the similarity of two of these images to get a similarity metric. So I think till now we have used cross entropy laws for classification, and that gave us good insight and good performance. But what we would now want to look at is also other non-contrastive losses. And does anyone here want to tell me how we use the cross entropy loss, or what does it give us? Okay, so cross entropy loss will basically give you like a probability value of all the classes. And I think Sarthak also mentioned this earlier. So that is what it gives us. But when we come to verification, we also want to see the similarity between these two feature embeddings. And so cross entropy does not really look at the similarity or dissimilarity aspect of it. And so we need contrastive losses in this case. Cross entropy is a non-contrastive loss, and it does not look at the similarity metric. But what contrastive losses does is it tries to group similar embeddings in a way. So it is sort of clustering, sorry. And this is what we want to do. We want to group the similar embeddings amongst the class more closer and make it more farther from the embeddings in the other classes. And this will help us better with verification. So how do we train models with such loss functions? So there are two approaches that we will discuss today. One approach is a joint loss optimization. And here, like along with calculating our cross entropy while training, we also look at one of these contrastive losses, which I'll come to in some time. And we take like a joint loss from this. This could be a normal concatenation, or we could also take a weighted sum and so on, and train keeping in mind both of these losses together. And this could be one way. Another way is we first train our model for classification with cross entropy loss like we have done so far. And then after it is trained, we take this model and then we fine tune it only with this contrastive loss. So you can actually use your best performing classification model in this case and take the feature embeddings, the weights of that model, and then further fine tune it with the contrastive loss. So these are some type of contrastive losses that we will be discussing, and there could be other contrastive losses too, which you can sort of research on your own and try. One of this very intuitive contrastive loss is the center loss, which is very similar to clustering, in which you have like one center. Even in the loss formula over here, CY1 is like the center. And we are basically trying to group these particular points in such a way that eh, these points are like closer to the center for that particular cluster and away from the other clusters. So you are sort of trying to minimize this particular Euclidean distance between the center and the points that belong to that particular cluster and maximize the distance between the clusters themselves. So this is something that is very intuitive and very easy. So this was the first application of that. But we also have some more complex contrastive laws, which look at a lot of other things. Triplet loss is one of these applications where you sort of sample three different images, one being the anchor and one positive and one negative. A better way to look at it would be through images. So you can sort of visualize it in this way. So if you were trying to compare or get a loss for one particular phase, an anchor would be one such sample of, say, phase one, and then positive sample would be the same phase as the one we are considering in the anchor, and it should give a positive value, like it should recognize it as being correct. And a negative sample in this case would be a phase that is not the same as the anchor. And we would then train our classifier through all of these and then get the embeddings. And then we would calculate the loss and trade it off in such a way that we minimize the loss between the anchor and the positive, and we maximize the loss between the anchor and the negative. So in this particular loss, it becomes very important for you to sample in a correct way, because in this first of all, we need to resample. That is an additive step. And apart from that, we also cannot just randomly sample these images, because we want to choose good positives and good negatives. Good positives in this case would be, say, something that is very, that is the anchor phase, but something that is difficult to figure out. So for example, over here, like he's looking towards the left side, and which could be sort of difficult for the model to learn, and we want to give it as a case so that the model learns to identify that. And we want the negative cases also be difficult. So we need to sample images which are sort of similar to our anchor, but we don't want the model to sort of learn that this is similar, and we want the model to contrast from it. So these are like, this is like one of the methods, but you will have to also look at how to sample these images. Then we come to sphere face. So Professor Bhiksha is also one of the authors in this paper, and this sort of also looks at the similarity. But as earlier we were looking at the Euclidean distance, we now look at the sphere space. And now, so we have like cos over here in the loss formula, if you can see. And so we look at the cosine similarity between these embeddings. And this is what sphere face does. Over here, like we have M in the formula. M is the margin, which we can come to a little later. But theta over here denotes the type of the decision boundary that we want to learn. So this will basically be the parameters that you want to train. So margin is something that you can set. And margin will basically tell you how differentiated you want your points to be. So if you see over here, when we range our values of M from 1 to 4, the points are much more disjoint with a higher value of M. So this is one of the parameters that you would like to tune if you're using sphere face. Something similar to sphere face is your cos face, which is basically the same thing, but now instead of looking at a sphere space, we are now looking only in the cosine space. And you can see like the formula for loss is almost the same, but sorry, yeah. I'm sorry, your question? I don't think that's a question. So okay.
Yeah,
So cos face is
Mike was on mute. I just muted him.
okay. Yeah. So cos face is similar to sphere face, but just in the cosine space rather than angular space. And we can see this difference in their formulas. So sphere face, cos face, and another loss called arc face are sort of similar. And if you try to implement these, you could experiment with either of them with only minute differences. So arc face, as I was saying, is also very similar to sphere face and cos face. And the difference here you could probably see is over here, the margin is subtracted after taking the cos of the theta by I. But in case of arc face, you are actually adding this particular margin in the cosine function itself. So here, like only minute differences between them, but again, like we have seen that this multiplicative angular margin in cos face was replaced, and this additive margin actually gave sort of better results. So again, these are all like different experimentations in all these different losses, and you might want to like experiment with any with either of them. So yeah, the additive factor actually was found to be better converging um, than like the sphere face, which is the multiplicative counterpart. But again, like depending on your cases, either could work better. So you could look at any of these losses. So yeah, that was the end of the verification part. Do we have any questions? Would it be worth trying to use these advanced losses for classification itself? I would think that we would perform better at least. So yes, thanks for reminding. I think that was the point that I wanted to cover. So when you are sort of working with these losses and you're trying to improve the performance and verification, what you're actually trying to do is get a better feature representation of the face itself. And so like if you're when you are trying to apply these losses, it will actually end up giving you better results for classification also, because now you're able to differentiate between these classes better. What kind of algorithm? Okay, I think that was an earlier question. Okay,
I'll just add on to this question. Okay, we're better to focus on finding the optimal architecture first. Yeah, so I'll just pick up the classification one first. So in classification task, we already have a fixed number of classes. And hence we are using something like cross entropy, because if we have a fixed number of classes, we can compare our prediction with what was the desired output. In the verification task, we have new classes or new users which are not part of the original classes. So now we are doing something more on this, on like from, if you were to visualize verification, we are doing something more on the likes of unsupervised learning. So you have more classes, many more classes. Now, can you cluster them into similar, like cluster similar faces together, and that way, and cluster different faces apart. So that way, you can cluster, if you keep on improving this, you can cluster every individual in a separate region of the space. So hence the losses in the verification are about, if you have the same person's two image for the same person, you will try to push them together into the same cluster. And if you have the face of two different people, you'll try to push them apart in the space.
right.
This may not be your strategy for classifying a fixed number of faces.
Yeah.
And the second question about whether we should look for the optimal architecture first or tune the hyperparameters. So I would say, because you have done homework one, in homework one, you had a similar problem. You were not sure what is the best architecture, and also you didn't know what would be a good hyperparameter options. So you are doing both of these things together. So use the same strategy that you would have used for homework one. But only the additional part for homework two is that you have much more content available on the literature. So with homework one, we're working with linear layers. We only had MLPs to work with. People don't use MLPs that much now and have moved on to bigger and better stuff. So which for you, it meant that you had to spend much more time and efforts into finding a good architecture. But in homework two, you have the blocks to begin with. So I'm not saying blocks are the best way to do homework two. Maybe ablations or simple convolutions could get a better result. We don't know that. You have to try that to see if you simply work with convolutions versus if you pick up some blocks and you mix and match blocks, how would things play out? And while you're doing this, you also have to keep on finding better hyperparameters. Certain hyperparameters might work for different architectures, so you might be able to converge them quickly, but certain hyperparameters might change based upon what architecture you're using. Going back to the previous questions, what kind of algorithm should we use when downsampling? So I would suggest start with homework to part one first. In part one, you'll understand the relationship between upsampling and downsampling versus the stride in a convolution. And so it's a very beautiful concept. It was covered in the lectures, but when you write down your own code, it will become much more apparent of how do you do downsampling, or even without using a specific downsampling function, can you simply do a convolution with a different stride, or vice versa? You only implement convolution of stride one, and you use upsampling and downsampling for a fractional stride or a multiple, like a 2, 3, 4 stride. So yeah, so if you once you do homework to part one, this question will become much more clear to you yourself. Answer from Nishan. Okay. Is regularization in the form of weight decay or dropout something that is generally used in CNNs? So regularization is used a lot in deep learning itself. So the concepts about overfitting and underfitting, many of these concepts actually come from machine learning, the traditional machine learning techniques, where the model will overfit very quickly. So if you are using some basic machine learning architecture, and if you keep on training it for more and more epochs, after some time, your test accuracy will become worse and worse over time. So if you keep on training it, things will become worse for you. Your training accuracy will obviously improve, but your test accuracy will decrease. In deep learning, you would have already, if you look at your ablations from homework 1, you'll see that if you keep on doing too many, if you keep training for too many epochs, your model will converge, your test accuracy will not improve, but it will not become worse either. And the same pattern you will see in homework 2 also, that it will flatten more or less. There might be some small variation, but it will more or less would have flattened. The reason for this is because even though deep learning, we have many more weights and it's largely a very over optimized optimization problem, over parameterized optimization problem, because we have so many more weights. Because we are using regularization, the model doesn't overfit, just like you would have seen in machine learning. It will not improve any further, but it will, because of the extensive use of regularization, because they put limits on how much the weights can increase, etc. We force the model to learn more generalizable aspects of the data and not strongly overfit on training. So yeah, I would suggest, if you want to look into further, I would suggest comparing the ablations that you can find on literature for simple machine learning architectures, so simple regression classification techniques, versus the same thing that you have done for your homework 1. Okay, biggest thing for me to learn would be how to understand how to combine blocks to create a functional model. So there are 2 ways of doing that. One is empirical, just like the residual architecture connection itself. The residual connection was an empirical finding. Later on, people try to understand from a theoretical standpoint why it works. So a lot of stuff in deep learning, you will try different stuff. And if you have, if you saw the last recitation slide, we talk about grid search, random grid search, etc. So those techniques will help you do like an empirical survey of your search space. And the other side of things is you read papers, see what theoretical background is being created for these techniques, and maybe that might give you some insights. So it's like you try to do both things, and hopefully things work for you. But yes, there's a lot of empirical work involved here. So if there are no more questions, I can probably move to the Andrew. Yeah, Jill, did you have something to add?
Yeah, I just had something to add, like for choosing the optimal architecture for the classification. So yeah, like if you take the approach to, like, from the verification point of view, so if you take the approach to where you train your classification model first and then fine tune with the contrastive loss, like yes, you want to come up with a good classification model so that you have enough so that the improvement is better with the contrastive loss. But again, you need to understand, like, the verification, the point is to learn better representations, like the image representations. That is like the point of verification. So for example, if you just like augment your data a lot and then train a classification model that reaches like 90% accuracy or something, but it is not yet able to represent the image in a proper way, then it's not going to give you better results for verification. So you need to understand, like, the point of both these tasks are different, although it can be linked. Yeah, I think that's it I wanted to add. You can go on.
Can you stop sharing your screen so that I can share?
Sure.
Thank you. So yeah, just wanted to show you this virtual Andrew thing, a virtual OS that CMU provides us. Up till last semester, it was not really good, because they had like a virtualized GPU, and the CUDA version was extremely outdated, so you can't really use any of the latest version of PyTorch in it. But now this semester, I saw that they have improved stuff a lot. So for example, if I just open the command prompt and do NVIDIA SMI, you can see that they are using a pretty good GPU. And you have 8 GB of GPU, which you can find from here. If you find this, like 8192, you divide by 1024, you'll find how much GB of GPU you have. And if you also look at the system information, you'll find that it has 32 GB of RAM. This is pretty good. And I'm not sure if you can train a 20 million parameter convolution network for in this machine. But definitely, if you're working with 10 millions of or something like that, and you want to ensemble, this can work pretty well for you. There's a caveat, or rather, there are a few caveats based upon how things. So Windows has certain quirks. Then when you make a virtualized OS, it has its own quirks. So I'll make a detailed post about it later, but I thought I'll just add this on a bootcamp because more people will see the bootcamp and you might miss the Piazza post. So first of all, one major thing is anything that you install in C drive will be deleted because this is the virtual OS. Once you log off, everything is deleted from C. Anything that you install on W, this is your own like Andrew ID kind of space. This will stay. This is persistent. C drive is temporary storage. So, and if you don't have like a more than 1 TB of free space in this W drive, maybe contact CMUIT. I have seen in one student's case, this was like 2 or 3 GB. So the trick is you install everything in W. So install, let's say, Miniconda. So your download function, so your download is inside W. So hence everything in the download folder will stay, is persistent. So you can install Miniconda, you can install everything, PyTorch and etc., create a virtual environment, everything. But once you log off, your Miniconda won't be available anymore. So if you search for Anaconda or something like that, you won't find the terminal for Miniconda. But it still is installed because you can see if you go to wherever you installed it, it still exists here, which means if you know how to use the command prompt, you can activate Conda. So this is like, for me, it's like instead of remembering big commands, you can create a bat file. Bat file is like you create a bash script in Linux. Similarly, you can create a bat file for Windows. So bat file basically has a list of commands that you want to enter on the command prompt. It's as simple as that. So the first thing we do is we call the bat file of Conda. So wherever you install Conda, go to scripts, and then there is a file called activate.bat. You just call that file, and then you can change to the W directory and go to wherever you have your homework code running, and you can activate your environment. And I saved this bat file itself in W itself. So whenever I open a new a command prompt, I'll just have to run this bat file, and the script will run and everything will be sorted, and I can directly start my homework code. Second thing would be install Jupyter Lab so that you have like a notebook interface. The advantage is you don't have to reload data over and over again. So in Jupyter Lab, because just like you're doing in Google Colab, once your data is loaded into your memory, you can focus upon iterating on your network and stuff without having to reload data every time. But if you're using .py files, every time something goes wrong, so there's a bug in your code or whatever, you will have to wait for the data to load all over again because you start from scratch every time. That's another thing. There is an issue of out of memory. So when you do an out of memory, like if you fill up the entire RAM or GPU in Colab, your entire environment restarts. It crashes and it restarts, which is a good thing. Here, your environment will just freeze because I don't think it has good checks for out of memory. So instead of restarting your code, your entire OS will freeze. So my recommendation would be to start your homework on Colab. Once everything is working, make sure you are not crossing the 8 GB GPU limit and 32 GB RAM limit on Colab at any point of your time. And once you know that for sure, you can do more ablations on this virtual machine. The good part is it's available to all CMU students. You don't have to pay for it. But just because you don't have to pay for it on a per hour basis, still use it, frugally. Don't just run random stuff on it because CMU IT might change the rules if you abuse the system. So that's just one new thing I wanted to introduce you. More or less, pretty much every homework we design might work on this. Like at least homework 2 and homework 3 you can work on this. Homework 4, once I test it, I can tell you more about it. There might be certain, PyTorch is implemented slightly differently in Windows. So there might be certain different error messages that you might see on Windows, which you won't see on a Linux machine. So for that, just make a Piazza post. We'll try to help you. You can also do a Google search and solve it yourself. but because I've been working on Windows a lot, so I can also help you with those bugs. So that's pretty much it. If you have no other question, we can probably say goodbye and meet again in the hackathon.
And yes, thank you so much. We went way beyond the time, but thank you for staying.
All right, we can probably stop recording now.